Okay, so I'm going to highlight keywords that you should have gotten from the Edpuzzle as well from just basic stuff that we've done so far in regards to first derivative tests and whatnot. So position. I am given the position function, meters, seconds. So this is similar to a AP level type of question where we're going to do justification and all that good stuff. And I'm trying to show you how to identify things that make it a lot easier. So the more you identify, your brain will kind of automatically get into that mode of what it is that you need to do to solve the answers. Okay? So other things that are important are instantaneous velocity. What can you tell me about that? So instantaneous velocity will revolve around what?
Speed at one point.
The speed at one point, not over an interval, but at the same time it's the derivative. It's not the, what's the other word? So it's the derivative.
Average.
The average. Okay, so average rate of change is secant, derivative is tangent. You with me? Those are very important as far as what these are asking, because sometimes you're going to be using the wrong equation and you're going to be using the wrong method with what you have. Okay, so here we go. So we have instantaneous velocity, particle at rest. We know obviously it's when the what is equal to 0? Derivative, the velocity function. So if I say that the derivative, sometimes the derivative isn't the velocity function. If I take the derivative of acceleration, it's the jerk, or you know what I mean? It could be something else. Just know that it's the first derivative of the position function. Otherwise, the velocity function. Okay? When I'm moving to the right, it's when the velocity is equal to greater than 0. So positive, right? And then whenever it's moving to the left, it's going to be negative. Justifying your answers is that justification. If I put it's moving to the right because f prime of x, or the velocity, is positive. Is that enough justification? Yes, it is, because there was no first derivative test or second derivative test. Okay? Again, what does the first and second derivative test aim to find? Relative max and mins. So relative max and mins is what those aim to find, not to be confused with concavity, not to be confused with other things like that. Those are exactly what those aim to find. They just find them different ways. Okay? Alright, so the displacement. This is another huge word in the Edpuzzle that I gave you. Displacement for you should be 3 words right now. What are they? Change in position. Change in position revolves around what function? The position function. The position function. So if I do the change in position, I'm looking at the position function itself, and I'm going to use the equation of the final minus the initial. You understand? The f of b minus the f of a. Okay? Alright, so another word that was very important, a lot of people missed this. Okay, so let's get back. The total distance traveled is something that a lot of people struggle with. The total distance traveled is basically everything that has been traveled, whether it's positive or negative. How do we do it that I showed you in the Edpuzzle? I take the absolute values of all these intervals. Okay? All these intervals are reflective of different changes of direction. If I have a negative velocity, what's my displacement? Positive or negative? Negative, right? If I have a positive velocity, my displacement is positive. But if I account for everything, I'm taking the absolute value of every single piece and then adding. What do you think the most common mistake that people do? They add before they take the absolute value. Don't add before you take the absolute value, okay? Because it's going to be wrong. What you're doing is taking the absolute value of what? The displacement. So, knowing what you're doing and knowing when you're doing it, that's what I'm looking at as far as you developing to say, what am I going to do as far as at this point in time or at this step? Okay? Alright, so find the acceleration of the particle. That's easy from what you've been given. What do? 2 derivatives, right? Take the second derivative, plug in the value of 3. Right? That's it. We'll get to the graph here in just a sec. Now, I'm not fully going to work this out. I'm going to do enough to where you've learned the concept and you could do the stuff on your own. But what I am going to use this time to do is to teach you how to be fast. Teach you how to be efficient with these calculators. Okay? This unit. If you aren't sold on these calculators yet, this unit should sell you on this calculator. You're going to see why here in just a bit. And I mean, you are a lot faster than someone using the 84. Okay? You might have seen hints of that in the Edpuzzle. I'll show you today in real time. When is the particle speeding up? What do I care about when I see speeding up? the absolute value of the velocity?
The signs are the same.
The signs are the same. That's the most important thing. Some people think I'm speeding up when it's the absolute value of velocity, or I'm speeding up depending on the sign of acceleration. No, it's none of that. What it is immediately to, in the way that we are learning, in the way that we are justifying here in calculus, don't use any physics methods. It will be when those two signs are the same. Okay? Let me give you a quick story. Okay, and we can record this. It's okay. So we live in a cul-de-sac, and we play football with the kids a lot. So there's maybe like 20 to 30 kids, and I'm usually the all-time QB because I don't like to run. So I'm going back, and this one kid is blitzing, and as I'm drawing back, what's my velocity right now as I'm drawing back? Negative. So I'm drawing back, and I trip a little bit over my feet, and I start stumbling, trying to catch my footing. And this kid, who's probably like 15 right now, but he was 10 at the time, sees that I'm falling. And instead of trying to catch me so I don't fall, he rushes to push me down. And we're on the concrete, we're on the street. So as I'm falling, what did he push me with? Negative or positive acceleration? Negative acceleration. In respect to me, it was negative acceleration. So what did that cause my speed to do before I hit my tailbone on the concrete? Increase. Do you understand? That's exactly what happened. It would be nice if he used positive acceleration to actually help me out, but he didn't do that, okay? So it's all about the signs. It's all about the signs being the same. If they're the same, they're helping each other, or if they're opposite, they're hurting each other, okay? Hurting each other being slowing down. Now I'm going to give you a little picture right now to see if you understand what I just said. Okay? Let's go here. Bear with me. So here we go.
Yeah, it's a spring.
So it's a spring with a weight. Don't judge my spring. Alright, and it's an oscillating spring. So I'm going, whatever. Okay? So as this thing is moving, I'm going to start time is equal to 0 at the bottom. Okay? And as I let it go, it obviously will go upward. You agree? Okay. When it oscillates forever and ever, it will come to a resting point. And the resting point will be called its equilibrium. Okay? So at equilibrium, it's not going to move anymore. Okay? So, now let's look at this. I'm going to take some moments in time. Here, 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 here. And we're going to call them 1, 2, 3, 4, 5. Okay? And on the way down, we're going to call them 6, 7, 8, and 9. Okay? Now, all we care about, Ethan, is what? The signs of what? What are the same? Velocity and acceleration. So velocity at a certain time and acceleration at a certain time. You ready? Okay. So as time is equal to 0 right now, basically where it's at, anyone, can you please tell me, let me move this over just a little bit. Can you please tell me what the velocity is? 0. The instant that I let it go, the instant, now think how small that instant is as far as duration. It's 0, right? What's the acceleration? Positive. Why is it positive? There's a force being acted on and it has potential energy. So it's ready to transfer into kinetic energy, which then it's going to catapult it into a positive direction. So that potential that he's talking about, that energy that's stored in the spring, has a positive acceleration. Okay? Now, this is if I'm looking this direction. True or false? True. Now, if I'm looking this direction, does it have a positive or negative acceleration? It has a negative acceleration. Do you understand? It's all about the perspective of the way I'm associated with it. So, I'm going to establish it like this, and I'm going to say positive. Is it moving? Right now, is it moving? No. Velocity is 0, right? Does it want to move?
Yes.
What direction? Positive. Forward, what are the other two? Right or upward, okay? So now, as soon as I let this go, and I go to 8, kind of envision that happening. What is my velocity? You have three choices: 0, positive, or negative. What is my velocity at 2? Sorry, is what I meant. It's positive. So 1, 2, 3, 4, 5, 6, 7, 8. What is the acceleration? Positive. Because those two signs are the same, what's happening in that interval between 1 and 3? It's increasing the speed. Okay? So now let's go to 3. Some of you are getting it. A couple of you are not yet getting it. What's the velocity? Positive. Still traveling what direction? Upward, forward. What's the acceleration? 0.
Oh, that's the middle.
Okay, for that instant. Immediate instant, the acceleration, 0. What is, well, we'll come back to that. I'll ask you here in just a bit what that means. Okay, 4. Let's go to 4. The velocity is positive. What's the acceleration? Negative. The acceleration is always pulling toward the equilibrium. True or false? True. Do you understand that? So it's always pulling toward that equilibrium. So if I have a positive and negative, what is happening when it's at 4? Slowing down. What's slowing down? The speed. Not the velocity. Well, we're going to say the speed, okay? The speed is slowing down, okay? Now let's go to 5. What's the velocity? 0. What's the acceleration? Negative. Why is it negative? Because it wants to move the other direction. The instant right after. So at this point you should see what's going on. Okay? So let's quickly go through this. 6, what's the velocity? Negative. What's the acceleration? Negative, so it's speeding up. 7, what's the velocity? Negative. What's the acceleration? 0. Okay. Now I'll ask you, what's happening there when the acceleration is 0 and you have a positive or negative?
It's all kinetic energy.
True, it's all kinetic energy. Okay.
No, not in 7, but in 3.
I didn't ever think about it like that. Let me verify on that. What I'm trying to get you to say is it's its fastest point. That's the fastest, that's its maximum velocity on that interval because it's going to oscillate and slow down throughout the entire interval. Do you understand? So on the very first one, if I said, where is the fastest velocity recorded when I let go of the spring? You would say what number? 3. What's the second fastest velocity recorded? 7, in the opposite direction. Do you understand? Okay? Alright, so here we go. Let's go back to this. This question right here. Let's go through this real quick. I am giving a position function. Find the instantaneous velocity. All I'm going to do, is take the derivative. Now, you saw this in the ed puzzle. They know what you're talking about. If you write s prime of t, or if you write v of t, they know you're talking about the velocity function. What am I going to do now? Plug in 3. The common mistake people make when they start learning the calculator is they plug in the value before they take the derivative. If I do that, what am I going to get? Nope. 0 all the time. I'm always going to get 0 because when I plug in a value, it's going to spit out a numeric value. When you take the derivative of a constant, it's always going to be 0. Please don't make that mistake. Okay, it's not always going to be 0. That should be a red flag to you of, I might have done this a little bit out of order. Okay, it's a common mistake. All right, whatever that is, I'll let you figure that out. What's your units? Meters per second, velocity, right? Okay, so B. When's the particle at rest? We already said when the velocity was equal to 0. Now, if I'm going to do this, chances are that I'm going to want to do a number line of some sort, okay? So finding the 0 of this is going to be 0 is equal to t squared minus 8t plus 12. What did I do just now? Factor out of 3, and I set it equal to 0 because of critical points, okay? Now I'm going to factor it. Anyone tell me what the factors are? Minus 6 and minus 2? Oops. You agree? So your critical numbers are actually what? 6 and 2. So part B, critical numbers are 6 and 2. What are your critical numbers if I said with C?
0.
0 and 8. 8 and 2 and 6, right? See what I'm doing? See how I'm kind of layering everything together? Okay? So if I wanted to do the particle at rest, when's a particle at rest? Anybody? 2 and 6. That's the only time when it's equal to 0. True or false? True, because if I put in 0 right now, what's the velocity when time is 0? 36 meters per second. Because I would put 0 into this velocity function. Okay? Alright, so let's keep going. Find the displacement of the particle in the first 8 seconds. We know there are 3 intervals. Let's test point these. Okay? Let's test the signs. What number would I test first, do you think? 1. And where would I put it in? What function would I? In the what? The derivative function. Okay? The derivative is this velocity one right here. So put it in 1. It looks like it's going to be a what? Positive or a negative? Positive. Good, thank you. Put it in, let's say 3. Those of you who, you could use a calculator if you want. Is it going to be negative? Okay. And then let's look at 6 to 8. Be positive, right? So looking at that, I know it's moving forward between 0 and 2 and 6 to 8. You agree? Okay. So is it moving forward at 0? It's already moving, right? So if I were to say moving right, I would say 0 to 2, closed open. Do you agree? Yeah, because it started moving at what? 36 is its initial velocity. It's already moving before you start your timer. Okay?
But if there wasn't a plus 36, it wouldn't have done that.
Correct. It would have been starting at a velocity of 0. Okay? Alright, and then it would be union, of course, 6 to 8. Do you agree? And then whenever you're at 8, would you close it as well?
No.
Why not?
It's just unlimited.
If I said, okay, I see what you're saying now. Okay, yeah, I didn't mean to confuse you. On part B, where it says moving right, you don't have to include it because it is going to be moving forever and ever after that. Okay, but if it did restrict you to 8, if 8 was listed up here, then you would close it and you would understand why. Okay? Now, let's go back to C. What kind of displacement do I have? Positive. So I don't really technically need to absolute value that interval, but I should, just so I don't make the mistake. Because here, if I forget, you're going to cancel some stuff out. Do you understand? Now, tell me, how do you do the displacement?
You don't do that with the
Final position.
Okay, so you're saying final minus initial?
Yeah.
Now, what does that look like? Tell me what I do.
S of 0 and then S of 8 and the original function. Subtract 9.
Okay, so he says S of 8 minus S of 0. Does that need to be in that order?
Yes.
Well, yes, it needs to be later time first, right? Final minus the initial. But he forgot to split it up in intervals. Because if you do it like that, what are you taking the absolute value of that we warned against doing? The displacement.
What did it say?
Yeah,
You said displacement.
Oh, my bad. I'm sorry.
What
I'm
did
sorry. I
you
see
say?
what you're saying. My bad. My bad. You're exactly right. You're exactly right. Kate, you're exactly right.
He corrected you. He corrected you. That's great.
I was confused when he said that.
Yeah.
Kate, you're exactly right. The answer is S of 8 minus S of 0. This would equal the displacement here. No absolute value necessary, right? But now, what I was thinking up here, not saying out here, the total distance has to be S of 2 minus S of 0, absolute value, right? Plus S of 6 minus S of 2, absolute value. You see it now? Plus, and so everyone was like, what? S of 8 minus S of 6, absolute value. There's the total distance traveled. It's always analyzing all the changes of direction and then making them all positives. Alright. I think the rest you pretty much can figure out. We've already done this before as far as speeding up and slowing down. You just derive again, and then you would stack their signs to see when their signs were the same or when they were opposite. Cool. Alright, so now for bonus points. Let me pause this. There we go. This is a good precursor to what we're about to do starting tonight. Optimizing functions. So if I came to you and I own this company and you're one of my workers and I said I want you to maximize the volume of a container. Okay, I want you to build a box so we can put, I don't know, some kind of robot in it that has maximum volume, and I want you to minimize the material that you're making it with. Because you'll minimize my production costs, which will maximize my profit and the fact that I'm able to fit more of that robot in that volume. Do you understand?
Yeah.
When you maximize or you minimize anything, you're going to take that anything's what? Derivative. There we go. First derivative test. If I'm trying to maximize acceleration, let's first obtain acceleration. Taking the derivative, my acceleration function is 3t squared minus 6t plus 12. This is what I'm trying to maximize. So I'm not going to treat this as the derivative already. I'm going to use the first derivative test of what I'm trying to maximize, and I'm going to find the critical points of the acceleration function. Okay? So a prime of t is equal to 6t minus 6. Setting it equal to 0, t is 1. You with me? So I just found the critical number for the acceleration. Again, how do I find the critical number? By taking the derivative of it and setting it equal to 0. This is a critical number. Something important is happening there. It's either relative max or relative min, or neither. Okay? So let's sign test it. This is a prime of t. Let's choose 0. If I put 0 in here, what's my value? Negative. If I put like 2 in there, what's my value? Positive. Does this show a maximum of some kind?
No.
No. Where can I find it?
Undefined.
The endpoints.
I was thinking.
At the endpoints where they are undefined.
Yeah, I was looking.
Okay? So the endpoints are what on this? 0 and 3. Some of you started off to do it. I need to use the candidates test. And what function am I going to put this into? A of t, because that's what I'm trying to find. What is the max and minimum values? So put a of t, I'm going to put 0. What would I get if I put a of t? 12? Wait, say again? So I'm putting it in this function. Okay, this is a of t. If I put 1, it's going to be what?
We should just pick things up.
9. And if I put 3, what am I going to get? 21. D is the correct answer. Me too. Alright, next part. Now, looking at this, again, I'm teaching you how to develop strategies with being able to identify what it is that it's asking so that it's easy to answer the questions very rapidly. Okay? So, this is, right off the bat, not a velocity graph. Someone asked that. It's a position graph, okay? S is just like F. The V will always be that velocity. Okay? So, probably a good rule of thumb, just to start off so that you know what you're looking at. This is the position function. Okay? And we want to know, when is the particle moving to the left? Now, moving to the left. As soon as you hear when the particle is moving to the left, what do you think I want you envisioning as far as justification? What is negative? Velocity. F prime of x, S prime of t is negative. Okay? So this is S prime of t is negative. But there's another way that I can interpret that.
Negative slope.
Negative slope. Okay, so negative slope. Because I like that. A lot of people use that as a quick shortcut with the graphs, and it works phenomenally. But no. Say again?
Different signs. Like
No, come on, guys. That can be 2 points. Almost. S of t is decreasing. Remember, it works the other way. One level up is decreasing or increasing, okay? So when you see this, it will be moving to the left, and I'll highlight it all, when this is moving to the left. It will be moving right when this is increasing. And it will be standing still on those intervals. Okay? Now, when I first look at this, what is the value, what is the position, think about this, what is the position at t is equal to 0?
Positive.
No, the position. Still 0, right? Its y value is 0. What's the slope at 0? What's the slope at 0? Try again. It's undefined. Muscles, why is it undefined? It's an endpoint. It's an endpoint. It's undefined because it's an endpoint. Do you see it? Alright, so if it's undefined, it doesn't have a velocity, but it has a position. Immediately after that, it has a velocity. You with me? Okay. Because there are subtle differences that you're going to see in the examples today. I want you understanding these subtle differences without having to do 20 problems to understand it. That's why I'm asking you the questions that I am. Yeah?
That's what I was gonna ask. So it's not moving left at 2, it starts moving left directly after 2.
Okay, let's go through them here in just a bit. I was going to wait till we're further down, but we can do it now. At 0, is it moving?
Yes.
Right at 0, is it moving? No, because it's an undefined slope, endpoint. At 0.5, is it moving? Yes, it's moving forward, right? Okay. And at 1, exactly at 1, does it have a velocity? No, because it's a cusp. Exactly at 2, no. Exactly at 3, no. Exactly at 5, no, because they're cusps. It's not moving. It doesn't even have a velocity of 0. The velocities of 0 occur at the horizontal lines. You with me? Okay. So now let's go through them. What is the velocity at 1.5? Okay, good. How about 2.5? So this first one was 0, and we were going to put centimeters per second. The second one is what? Negative 4 centimeters per second. What's v of 4? 0. And what's v of 5? Undefined. Undefined, right? It doesn't have one because it's a cusp. See it? Alright. Next part. I know it's been a while, but you need to recall this pretty quickly. The velocity function now, if I were to graph it, it's the derivative function of this. Okay? Here we go. What's the derivative, i.e. slope, between 0 and 1? No, what is it? 2. So y value wise, I'm going to show something that has a y value of 2. Throughout the entire thing, because it's constant. Alright? Good. 1 to 2. 0. Why am I doing open endpoints? Because they're cusps. Non-differentiable, right? Let's go 2 to 3. Negative 4. 3 to 5. Wait, what?
Alright,
0, right? Common mistake, that is 1. And 5 to 6. Negative 2.
Yeah.
So this, what I just graphed, is the velocity. Now, if I were to graph the speed, what would change? The ones on the bottom would do what? Absolute value. So this would go up here to 4. This would go up here to 2. Okay, that's speed. And then finally, I know it's not being asked, but I'll ask it right now. What if I asked you to graph the acceleration? It's 0 throughout, right? Open or close dots? Still open. Okay? Because of the fact that this is a jump discontinuity at 1, it would be like, oops, let me get a different color.
It would just be like
Yep. So there, open circle, again, the whole thing, and then here. That would be the acceleration function. Because they're all slopes at 0 with those cusps. Jump discontinuity showing non-differentiability. Yeah.
So if you get like a position graph that doesn't have any like concave up or concave
Say it one more time.
If you, on a position graph, if you don't have concave up or concave down, is there no acceleration?
Yeah. Nice. You just reminded me of something.
Of course it is.
Of course you did.
This is solved like 8 seconds.
Velocity graph. Interrupt around your brain. Velocity graph. Now let me fix something because something's wrong. Chill. Alright, so velocity graph. Now, looking at this, when am I speeding up? Wait, what?
When it's above 0.
When it's above 0. That's what he says. Any other?
When it's above 0 and
When it's above 0 and increasing. Come on, they didn't show you this.
When it's
Oh, if it's
increasing.
speed, it has to be above 0.
Okay,
I think he's right.
there's a shortcut. You physics people should know what I'm talking about.
When, I think I
repeat the question.
Okay, okay, here. I'm looking at exactly, that's what I'm wanting to show you with that. It's a velocity graph. What is the shortcut? I mean the very shortcut that would tell me on what intervals is the speed increasing. It's moving away from the x-axis. Okay? If it moves away from the x-axis, what does that really mean? It means the following. Look, that means it's going to be speeding up here, and it's going to be speeding up here. Let's analyze why. On those intervals, first of all, let's do the first one. If I took a tangent on this first interval right here, what can you tell me about that tangent? Positive. What's the velocity there? Positive because it's what? It's positive because it's above the x-axis, right? The slope is positive because it's increasing. Like you could see the slope is positive, right? But the y value of the velocity function is positive because it's above the x-axis. Two positives make it speed up. What kind of slope does this have? Positive or negative or 0? Negative. What kind of y value does this have velocity-wise? Negative. That's why it's going to be speeding up, just in the backward direction. Okay? And then, look, check this out. These is when it's slowing down. Because, let's look at this first interval. What's my velocity? This is a velocity graph. It's a positive because it's above the x-axis. What's my acceleration? Negative. Two ways I can see that the acceleration is negative. The negative slopes, but also because v of t is doing what? Decreasing. Who said that? Harrison. Decreasing. So if I know that, and we were talking about this earlier, that the velocity is decreasing, remember that chart we did this with? That means the acceleration is what? Negative. Decreasing, negative, and then that concavity. Remember that table, whatever that we did long, long ago? Okay? Now let's go to this one. A car is traveling on a straight road 24 seconds. This is a velocity function graph. Meters per second. Now what I want you to do is tell me what's the derivative at 4 of this graph. It's undefined. Why? It's a cusp. What is the derivative? Careful, at 20. No, it's not undefined. It's not the cusp. It's weird, huh? You guys are trying to figure it out. Look, look, look. Go straight to what you learned long, long ago. Yeah. So this point is 24, 0. Ready? y2 minus y1 over x2 minus x1. Whoops. Negative 5 halves. Negative 2.5. The acceleration is negative 2.5 or negative 5 halves what? Meters per second squared. Because right here 20 is within the interval, not on a cusp. Okay? Are we good? Alright, so let's go for this one. Let me ask you this. If this is a velocity graph, what's the velocity right at time t is equal to 0?
The velocity at
0, right? What function am I looking at will determine what do I interpret. The undefined part because it's an endpoint, or the y value part of 0 because it's the function. There's a lot of that everywhere with VAP exam. Okay? Alright, the car's acceleration at time t in meters per second between 0 and this. Write a piecewise. No, that's too easy. Let's go to C. Find the average rate of change from 8 to 20 seconds. What'd you do?
T of 20 minus T of 8. But
Connect them, connect the points and take the slopes of the line.
so V of 20 minus V of 8.
He's saying V of 20 minus V of 8 over 20 minus 8. Do you agree? He's saying this is the average rate of change of V. That's exactly how you do it. Because you're saying the average rate of change of V, V is your position function. So when you want to find the average rate of change of a function, it's f of b minus f of a over b minus a. You understand? Okay. Almost done. One more AP style problem, and then we'll go to your CFA. Okay. Actually, you know what? I forgot to show you calculator stuff. Get your calculators real quick. Here comes the calculator stuff. You'll be okay. What I want you to do is I want you to put s of t into the function, or into the calculator first. Here we go. Follow me, and if you're not sold on this, follow us and you'll be sold on it, I guarantee, after today. T cubed minus 12t squared, and technically you can use two calculators. So those of you who are like, no, I want my 84, you can use that as well, and use this whenever it benefits you most. So here we go. T cubed, okay, and it's going to be minus 12t squared plus 36t, and the end is, oh, that's it. Okay, so this right here, I'm just going to press enter. I'm going to now store it. What do you want to store it as? We could do f of t, we could do f of x, we could do s of t, whatever you want. Let's just go ahead and do it as it looks like, okay? S of t. So I'm going to store it as s of t. Okay? The reason why I did that, I put the function in there first, press enter, then I controlled, stored it. The reason why I did it now is because let's say that we want to know the velocity at a given point. If I want to know what is the velocity after 3 seconds, what can I do with what I have stored right now? Take the derivative and evaluate it at 3 seconds. Now watch. Two ways to do it. You tell me which one's correct. This button right here, I'm going to take the first derivative and I'm going to put what letter right here? T, because that's what I'm in respect to. So T, and I want to know whenever it's at 3 seconds. S of 3. This is what people would think. What is my answer going to be when I press enter?
It's going to be the displacement.
It's going to be 0. Because what it's evaluating is the velocity first, and then the derivative of a constant is 0. That is wrong. So what we need to do, learning how to use a calculator, is press menu, calculus, or 4. Press 2 for derivative at a point. This will do it in the correct order. I started the notes off today saying this. My value is t. Or, sorry, the variable is t. My value is at 3 seconds. I want to know the velocity, so I'm not going to change this to the second derivative. I'm going to keep it on the first derivative. And when I look at it, it looks like this. It looks a little different than what the other one did. What do you think I'm going to put here? S of t, not S of 3. Okay? So here we go. S of t, boom. Now, this is fast. What do I want you to do on the test next week? I want you to show this work right here. So this, you'll be whoops, you'll need to show as far as writing it on your paper. And show that it's equal to -9. And you can even say right here, if you wanted to, this represents the velocity, so meters per second. Okay? Other people who don't have this calculator, they're going to actually have to find what it is, and then they're going to say S of whatever, or S prime. So those who don't have the calculator, they first have to find S prime of t, whatever it is. Then they'll do S prime of 3, and then they'll write the answer. You go quickly to it and you have it stored. The reason why it's cool that you have it stored is because of the fact that you can now go back and say, well, I don't want to look at that. I want to look at the acceleration at 3. So I'm going to say menu for derivative at a point. The input value variable is t at 3, but this time I want to know the acceleration. Look how fast this is going. S of t, my acceleration is -6 meters per second squared. With these two numbers, very quickly, I can see that the particle is doing what? Speeding up. You see what's going on? This is so convenient as far as how you're able to do this. Otherwise, you have to look at a graph and see when it's moving away from the x-axis. You know what I mean? There's a lot that you're layering. When I've shown you before, you have a velocity function here. You have an acceleration function here. And I'm like, remember when you had different ones and you have positive, negative, positive, positive, all this work you're bypassing. You're doing it with the calculator. And if it's a calculator problem, I want you to be able to do it that fast. Do you understand? And for statistically, since we started using these calculators, we're really fast on the calculator part. Really fast. Like, it's kind of boring. People might even put their heads on their desk, just sleep a little bit after they're finished. And no joke, it's really fast. Yes? The integral check for displacement? And sure, yeah. No one asked that this morning. Yeah, I'll definitely do it. The integral check, yes, you can use it on the test, but you got to show the work the other way, okay? You can use it to check your answer. Here we go. Always, when I want to know what the displacement is, it's the integral of what function? Velocity. Okay? Only velocity. So I'm going to say this is the integral right here. And when I press enter, I can say between 2 and 5 seconds. And let's say the velocity function, let's just make one up. What do you want to make up? 2t squared minus 5? Okay. So 2t squared minus 5. What goes here in this box? T. Good. Because that's what it's in respect to. When I press enter, the displacement... Wait, say again?
Wait, no, that's for total distance.
Yeah. So the displacement, because I said 2t squared minus 5 is a velocity function, we just threw it out there. The displacement is 63. So if the velocity is meters per second, this is 63 meters is what it's been displaced by.
Then if you do absolute value, it's the total distance traveled.
Then it's the total distance traveled. That is different because it could change direction sometime throughout the interval, okay? So let's do that right now. Because we don't want to do every single one and then add them all up. We'll have to do it for the test, but we can quick check it this way. Okay, so quick check it. I can come up here. I can copy it. Go to the beginning. And I can say the absolute value. And you can find that right there. And I might have to rewrite it. Yeah, so 2t squared minus 5. Let's just delete this. You see the difference? And again, what is a common mistake people make probably when they're doing this quick check? They take the absolute value after the integral. Okay? And you'll understand why that works when we get into integrals. The absolute value is inside the integrand. Okay?
So the first one without the absolute value sign about the displacement, and the second one with the absolute value about the displacement.
Yeah. And in this case, they're the same. Can they be the same? Yes, they can, because they could be traveling in the same direction the whole time. Okay? Alright. So going back, well, yeah, I just showed you. Now let's go back to our last problem, then we'll have our CFA. This is a modified version of Form B, which is the more difficult test. That's if you're absent for the first one. The Form B is the one that you make up, your makeup AP exam. It's modified from 2009. This is a velocity graph. Okay? You are to interpret this as x and y. So the velocity of a particle moving along the x-axis is modeled by the following differentiable function. This just means that I can take the derivative, guys. That's all it's saying. Okay? There aren't any cusps. It's differentiable everywhere. Okay? That's important but subtle. Where the position x is measured in meters and t is time in seconds. Use the data from the table to estimate. There's another key word, and I was highlighting keywords at the beginning that will tell you what it is that you're going to do. You're trying to estimate the acceleration of that table. How do I do that? What's the average rate of change of velocity? Acceleration. Is it exact acceleration? No. It's an estimated acceleration. What's the average rate of change of position? Velocity. Is it exact? No, it's an average. Do you understand? Okay? So when you see rate of change, it feels like a derivative. It's just, am I exact or am I approximate? That will tell you whether you do the, okay, so exact is to, exact is to, as approximate is to what? Come on, 2 points. Exact is to tangent, as approximate is to secant. Okay? So that's exactly what I'm wanting you to think about. Exact is to tangent, whereas approximate is secant.
Never got that.
Okay, here we go. So how do I do it? I'm looking for 36 seconds. The fact that it's not listed says that I really have to pay attention to this one. So all I'm going to do is do an f of b minus f of a, or y2 minus y1 over x minus x1. Okay, which you did way in algebra 1. Okay, so here we go. What would I write? No, y. The y is on the top. So 7 minus negative 4 over 40 minus 32. So we have 11 over 8. So this is 11 over 8. What would the units be? Yep, meters per second squared. This is the estimated acceleration at 36. It can't be exact because I'm not even given a what? An equation. I'm not given a function. Okay, so let's go to B. From 0 to 40 seconds, must the particle change direction in any of the subintervals indicated by the data? If so, which one, and explain your reasoning. Must the particle change in direction? Where?
8 to 20, it starts going up.
So right here, it's going to change directions, right?
And then 32 to 40.
And then 32 to 40, it's going to change directions. Okay? Would you agree? Yeah. And because of the fact that the velocity changes signs. All right. Based on the values, what is the smallest number of instances that the velocity could equal -9? Where's that one that you say?
In between 20 and 25.
Wouldn't that be like 4?
There's 2 in between.
Or 3 and 25.
Oh,
So you said here?
And 8 and 20.
And 8 and 20? And is that it? That's it, right? Okay, so 2. And justifying it, showing that it would fall within that interval. We'll learn a little bit more of what that's looking like justification-wise, but it's not relevant now because you're not going to be tested over it. Just the concept, you will. All right.